going to be doing the last half of related rates. And the related rates questions that we have still to do are the application ones, right? The ones where you're given a story and you're being asked to, solve. And typically you're going to be asked to find a missing rate. And so I've got a little hit list of the 5 steps that you would use to do this. You don't really need to bother writing these down frantically, because you can always go and watch the video, can't you, and pause it and write it later. But essentially, this is a kind of menu or a template for how to approach application questions. Not every step is involved in every single application, but most of them will use most of these, if not all the steps. So the first step is identify the variables in the problem and call them anything you like. But I like calling things X, Y, and Z because I'm pretty boring. But you could call, if something's a height, you could call it H, right? And if something's a width, you could call it W, things like that. But I just basically, if it's something that's horizontal, I'll call it X. If it's something that's vertical, I'll call it Y. And if it's something that ain't those two, I'll call it Z. So that's essentially the way I label them. But the labeling is totally irrelevant. You still get the answer no matter what you call it. So you have to identify in the story what the variables are. That is, things that are going to change through time. Because all these stories, everything is moving in respect to time. Everything is changing size, getting bigger or smaller, but all through T time. Then the second step is create a formula that connects all the variables together. And the types of ways you're going to do that is that if you see a right angle triangle, then there's probably going to be a Pythagoras formula. Sometimes they tell you what the formula is, it's a volume of a sphere, in which case you just do 4/3 pi r cubed, or a surface area formula, or I think one of them's an area triangle. And similar triangles you sometimes use rather than Pythagoras. And one of the questions we're doing today involves using similar triangles to create that connecting formula. So once you've got that formula, maybe it's x squared plus y squared equals z squared, right? Whatever it might be. You then differentiate that formula from here with respect to the variable t. So we've done a lot of that yesterday. So if it's an x cubed, you get 3x squared dx by dt, right? That type of thing. So differentiate all the guys from this formula, right, with respect to t. Then in step 4, substitute all the variables, substitute numbers for everything, right? For the x, for the y, for the z, for the dx by dt, the dy by dt, right? Everything that you know, put in a number. And when you do that, there should only be one thing that you don't know, because that's the thing you've been asked to find right at the beginning. So you'll be finding dz by dt or dx by dt, or whatever it might be. And that's what step 5 is, to solve it. So that's kind of the general process. I didn't have a lot of time, but I did have time to write down some of the questions, so I don't need to do that flip back and forward thing. But I've only got, I think, about 4 of those, so after that I'm going to be flipping back and forward, or at least I'll read the story to you, which is more likely. So here we have an example of that type of puzzle. The altitude of a triangle is increasing at the rate of 1 centimeter per minute, while the area of that triangle is increasing at the rate of 2 square centimeters per minute. The units are to keep the engineers happy, but really the 1 and the 2 are important for me. Then we have the question, at what rate is the base of the triangle changing when the altitude is 10 centimeters and the area is 170? So that's pretty much everything we need to know is tied in here. Now, a few important little details. If something is increasing, it means that number is positive, as it obviously is. But if they had said the area of the triangle is decreasing at this rate, we have to realize that that means -2. So if something is getting bigger, the number is positive. If they tell you something's getting smaller, the number is negative, because they won't tell you it's -2 or +2, they'll just tell you it's 2, and you have to look at context. So if something's increasing, it's a +2. If something was decreasing, remember to use -2. That, if you get that wrong, you'll end up with the wrong sign when you're finished, right? Your rate might be -2 when it should be +2 or vice versa. So identify the variables in this problem, and I'm going to call them X, Y, Z. So they're talking about a triangle. So I'm just going to draw a triangle because I think visually that helps. I have this guy. I have this guy. The guy that's the bottom is the base, and I'm going to call that X. This is the altitude. I'm going to call that Y. And obviously, the other variable is going to be the area. But in this case, I'm going to call that A. So I now need a formula connecting them. So there's my three variables. A for area, 1/2 xy. You're all happy about half base times height becomes a half xy. Now, if you don't like x and y, couldn't you call it a half bh and make that b and make that h? And the math would be exactly the same. It wouldn't change a darn thing. So I guess what we've done here is step 1, and this is the create the formula, step 2. Now we need to differentiate this guy with respect to t. Differentiate a, you get dA by dt. Do you recognize that since these two things are multiplied together, if I want to differentiate it, I'm going to have to use a product rule. So it's going to be f dash j plus f of g dashed. So dA by dt. Right. If you differentiate with respect to t a half x, technically don't you get a half times dx by dt? Right. So if you differentiate a half x with respect to t, you get 1/2 dx by dt. Times g, which is that guy, plus, leave that guy alone. And if you differentiate y with respect to t, technically don't you get 1 times dy by dt? So we just call it dy by dt. So I have just differentiated this formula, right, with respect to t, and it's okay, it's not that ugly, but it's a little bit messy. So what I'm left with now is to substitute all the numbers, and sometimes you have a little bit more work than you think. What have they told me here? Well, let's see. They told me the area is 170. Check. They told me the altitude is 10. So they told me this guy is 10. They've also told me that the area is increasing at the rate of positive 170. And they also have told me that the altitude is increasing at 10. I've been asked to find the rate at which the bases change. So I'm being asked to find that guy. Have you noticed that there's one number that I need, and that's I need to know what x is. Now, it would have been nice if they just said, you know, the base was 20, the height was 40, and the area was whatever, right? But they haven't. And remember yesterday when I tried one and it didn't work? This one's going to work. So I'm going to be plugging in numbers for all of these things except for one guy, that guy, right? I'm here. Well, that means I'll need to know that number, which I do. It's 170. Oh, wait a minute. Let's check my story. That's not 170. The rate at which the area is increasing is 1. Okay, so that's 1. Now, I know that guy is 1. I don't know that guy. I know y is 10. I have 1/2. X is missing for a little while, times 10. Do you see why I need to know X? Right, I need to know that number. So I'm going to go back to my formula, which is 1/2 xy. I'm going to use the fact that the area is 170 and that y is 10. So that gives me 170 is 5x, and divide there. Do you see that the x value was kind of hidden from you? You had to find it separately. Rather than just telling you what it is, which would be nice, they hid it from us. So that means this guy here is 34. So we are at this point here. So we've just differentiated. And the last part is solve. Well, that's the guy I'm trying to find. So let's see what we have. 1/2 times that times 10 gets me 5 of these guys. 1/2 times that gets me, what does that get me? That gets me 17 times. And I did it again, didn't I? That's 2. It's my scanning. I have no excuse. It's just my scanning. Right. There. We're okay now that I've got the right number. And what do we have? Subtract. And then divide. And it looks like I'm going to get negative 33
34,
divided.
Professor.
34
You
here.
wrote 33.
I'm subtracting it from both sides.
Oh,
So 1
my
take out
apologies.
34. No, it's worth checking with me. I'm okay with that. Negative 6.6. So that would be the rate at which this side is shrinking in. So if that side's getting bigger, this side is kind of shrinking in to make up for it. And moral of that story is, when you're reading a question, you have to make sure that you match the numbers up properly. Right? If you notice that I put these down and then repeated them there. And that's because I've only got one good eye. And when I read questions, I scan and then I come back and I scan in the wrong place. So it's hard for me sometimes to do that properly. But we're done. I guess the units are important here for the engineers amongst you. So there you are. And that, the process was fine. Kind of screwed up a little bit in other places, but not there. Now, each question should be looked at on its own merits, because they're not going to be the same as the previous one. They're always going to be something a little bit different. This one here is a spotlight on the ground, shines on a wall or a building 12 meters away. So I'm going to imagine that we're here and here. And what do I know? I know that from here to here at least is 12 meters. And there's a spotlight here. There. That's a spotlight. A man is 2 meters tall, walks away from the spotlight. So here is a man. And the spotlight casts a shadow on the wall. And I know that the height of this man is not going to change, right? He's 2 meters, he's always going to be 2 meters. So that's not a variable, that's a fixed. But as he's walking, won't that shadow change, right? You know, if he was not that distance, but he was here, we'd have a different kind of shadow at each point. And, you know, imagine the man was here, right? Wouldn't the shadow be really tall? Imagine that man was here. Wouldn't the shadow, the height of the shadow, be different? So this is a variable. This changes. Since the man is walking away from the spotlight, won't the distance from here to here also be changing? So there are my two variables, x and y. X represents the distance that the man is away from the spotlight, and y is going to represent the height of his shadow. Right, now they give us some information here that I'm going to factor in a moment. But the first thing I'm going to have to do is figure out a connecting formula. And I know it's a right angle triangle, which tends to mean use Pythagoras, and there's lots of situations where that's true, but not this one. This one is going to be similar triangles. And I don't know the last time you've done similar triangles, but basically it says this. If you have two triangles which are essentially similar in shape and they only differ in size, we call them similar triangles. Now, in this triangle here, the little baby one is 2 meters by x. 2 meters by x. Now, the big triangle, that distance there is y, and this distance here is 12. Are we good so far? So if I know anything about similar triangles, there's a property that says that corresponding sides are in equal ratio, which basically means that guy divided by 2 is the same as that guy divided by x. Are you comfortable with that guy? Now, that is the formula, but I'm going to make it look pretty. Yeah. Cross multiply and then divide. So this is the formula that is connecting the two variables x and y together. Are we comfortable about that? Now, could I have left it like that? Yes, I could, but that one I think is easy to deal with, so I will use that one. So identify the variables. Well, we have, they're called x and y. Create a formula that contains them all. Done that. Step 2. Now I'm going to move on to step 3, which is differentiate your formula with respect to t. So if you differentiate y with respect to t, you get this guy. If you want to differentiate this guy with respect to t, won't we have to differentiate that first and then finish with the x by dt? So I'm cutting a lot of corners here, but are you happy with that's what you would end up with? If you differentiate 24 over x, which is this guy, you get negative 24x to negative 2, you get that bit. And then you finish with the x by dt. So far, so good? Right, now, I haven't used some of this information, so I guess I should start using it now. If the man 2 meters tall walks from the spotlight, the wall at a speed of 1.3 meters per second. So you've just told me that dx by dt is 1.3. How fast is the length of the shadow? So you've just asked me to find the rate at which dy by dt is changing when he is 4 meters from the building, when x is 4 meters. Right, now if you look at the information that they've told me, plus the thing I'm trying to find, dy by dt then is negative 24 divided by 4 squared times dx by dt. And we're going to be doing it to what, 2 decimal places. So here it goes. Negative 24 times 1.3 divided by 4 squared, which is 16. And the answer I get is negative 1.95, and I believe the units are meters per second. So what that's telling me is, as this guy moves towards the wall, won't the shadow get smaller? And it will get smaller at roughly that rate. Smaller because it's negative, right? If it was plus, it'd be a different story, right? But the shadow would be getting bigger. Now, if you think of what we did with that question and what we did with the one that came before, right? There are similarities, but there's just as many differences, isn't there? Wasn't this Pythagoras? This was similar triangles. Wasn't there a product rule going on here? There wasn't really a product rule going here, but weren't there find values and plug them in? In this one, didn't we have to find a missing x? In this one, it didn't matter because there was nothing missing. You know, so each one has its own little flavor. Sometimes you do something like you find a missing x. Sometimes you don't need to. Sometimes it's a Pythagoras that connects them. Sometimes it's something else. So each question really needs to be looked at on its own merits. So let's move to the next one. A snowball melts so that its surface area decreases at the rate of 3 square centimeters a minute. Right, so I've got a big, you know, ball, right, snowball, sphere, and it's shrinking, right, because the sun's melting it, and it's shrinking, and they're talking about the surface area is shrinking, right? So, yeah, it's decreasing, but they're doing it in terms of what the surface area is doing. And find the rate at which the diameter is decreasing when the diameter is 11 centimeters. So, in this question, really when I'm identifying the variables here, I think I'm going to use D for diameter. Now, I also need, in this particular question, a connecting formula. But it's not Pythagoras or similar triangles. I know the formula for, I know the formula for the surface area of a sphere. It's 4 pi r squared. And in an exam, I would tell you it was 4 pi r squared, but you would, in your homework, go hunting for it, right? And that's a problem, because that formula doesn't use diameter. And since this is in terms of diameter, I need my formula to have D in it. But I do know something about the diameter. Isn't the diameter twice the radius? Which is another way of telling me that the radius is half a diameter. So what I end up doing is I have to adapt this to 4 pi times half a diameter squared. So it's 4 pi times 1/4 d squared. And then we end up with the connecting formula. So in this case, aren't there really two variables, surface area and diameter, right? So that's probably going to be a little bit nicer. So I've got my connecting formula. Let's differentiate with respect to t. If you differentiate that guy, you get this. And that's basically 2 pi d times dd by dt. And that wasn't too bad. That wasn't really that ugly. Now, if I read up at the top here, and what have they told me? They told me that its surface area decreases at the rate of 3. Now, notice I'm writing -3, even although there was no negatives anywhere. But decreasing at the rate of 3 means, yeah, it's easy just to see the 3 and not pay attention, right? -3. And what else do I know? The diameter is 11 centimeters. Right, so basically I should be able to solve the problem then. This guy is -3, 2 pi times 11. That fella, right? So -3 is 22 pi. And so -3 divided by 22 pi is the guy we want. And they want the answer to 3 decimal places. So -3 divided by, put a bracket around it, 2 pi, and I should have called that 11, which I kind of forgot to change it back. It's about -5 point, what do we want, 3 decimal places, 252. There's our answer. -5.252. Yes.
Should that not be 22 pi, not 2 the way you had it?
Ooh, 22 pi. Let's check that out. -3 divided by 22 pi. And it's a totally different answer. So it's -0.428. And that's me just being careless. Because it is there. And then it kind of disappeared. So we've seen 3 different questions, and none of them have been really exactly the same as the other, right? Wouldn't this one qualify as the connecting formula is a formula that you know? The one before that was similar triangles. The one before that was Pythagoras. And this is the last one that I've actually got written down. After that, we'll just have to do the look at the screen kind of thing. Ooh. A plane is flying at an altitude of 1 mile. Okay, so there's the ground. Here is my plane. That's at least what it is. Here is going to be my radar station, which they talk about. And this distance is not going to change. It's flying an altitude of 1 mile. And this is going to travel in that direction. So I'm going to call this distance x. And dx by dt then would be the speed of the plane, which is 420 miles per hour. It says, find the rate at which the distance from the plane to the station. So imagine some time's gone by, right, and it's now here. Then this distance here is going to represent the distance from the plane to the radar station. Does that make sense? And won't that change, right? As the aircraft travels, that distance will change. And I'm going to call that guy Z, because I like to call vertical things Y and horizontal things X, and everything else I'll call it Z, unless there's another letter that makes more sense. And we've defined the rate at which the distance from the plane to the station is increasing when the total distance is 4 miles. So when Z is equal to 4, essentially, right? Total distance is 4. Well, I've identified the variables, right? There's an X and a Z. I've also written down some numbers that you tell me. Now we need to figure out a formula that connects these 2 variables together. If I draw a little corner symbol up here, can you see a right angle triangle? You see a right angle triangle here? So we're going to do the Pythagoras thing. And Pythagoras says that Z squared is equal to X squared plus 1 squared. So that makes Z squared, X squared plus 1. Are we comfortable about the connection between the 2 variables X and Z? Pythagoras does the job. Any questions so far? Are we still with this question? Right. So you know what's going to happen next, isn't it? We're going to differentiate with respect to time. So if you differentiate z squared, you're going to get 2z dz by dt. If you differentiate this, you're going to get 2x dx by dt. And differentiating numbers gets you nothing. So I now have, just rewrite that again. We're now here, which is essentially step 3. Now, 2 times z, which is 4, times dz by dt is equal 2 times x times dx by dt. Oh, we have a little issue, don't we? Don't I need to know what x is? Now, if you tell me that z is 4, and I build a little miniature version of what's going on here, then won't this be x, won't this be y, and won't this be 4? And can I just tell you that it's the square root of 15? And you know where it's coming from? Right, just solving with Pythagoras. And so, there. So wasn't this another example of one of the variables was sort of a missing, although you were told enough information to get its value? You had to just, like, in this case, make a little right angle triangle. And if I want to find dz by dt, then I would just multiply all of this together. I'm not even going to bother. I'm just going to write down what it would be. It would be that guy divided by 8. Right, 2 times 4 is 8. And now I'll get to the calculator, and I'll go 2 times the square root of 15 times 420 divided by 8. And they want the answer to the nearest whole number, so that rounds off to 407 miles per hour. Are we slowly getting a feel for the process? Right, you're going to have a story. A lot of the time, pictures help. You're going to connect all the variables once you decide what things are variables as a single formula. You're then going to differentiate it. You're then going to plug in everybody that you know, and there's only going to be one thing missing. And then you solve for that one thing that's missing. That's pretty much the general theme for all of these questions. Any questions before we move on to our next one? Are we good? Right. Next one, you're going to have a little bit of problem because I didn't have time to write it down, so I'm just going to read it to you. And you can look at it yourself, you know, when you get to the homework. At noon, ship A is 150 kilometers west of ship B. So I'm going to draw the picture. And that's where A is going to start, right? And that's where B is going to be. And so A is 150. So that is a fixed number, right? From there to there is 150. Ship A is sailing east at 30 kilometers per hour. So this is A, and it's going this way. And I'm going to call that distance x. And that makes dx by dt 30 kilometers an hour. And ship B is sailing north, so it's going to sail that way, and I'm going to call that distance y. And the rate at which it is sailing, I'm going to call it dx by dt, and that is 20 kilometers per hour. And here's the question. How fast? Just another way of finding the derivative. is the distance between them changing at 4 p.m. Now, in case you didn't pick it up, this story started at noon, right? So I have a lot going on here, and I haven't quite created all the picture. Because if you imagine this as being a snapshot in time, then the distance between the two boats will be that distance there, right? And I'm going to call that guy Z. And I'm going to add an extra line this way. So I now have a triangle, which I'm going to redraw, that looks like this. That guy is Y. That guy is Z. But this distance from here to here is not X. That's this distance. What is the distance from here to here going to be then in terms of X? And your clue is the whole thing is 150 and this piece is X. So what's the other piece?
150 minus X.
Can you see that we have now got three variables, X, Y, and Z? We also have a connection, at least right now the connection is a triangle, but won't that turn into Z squared is equal to 150 take away X squared plus Y squared? You agree? Pythagoras is the connecting. Now, since I have three variables, I know I'm going to have to find out what those guys are equal to. I'm also going to have to either find out what these three derivatives are equal to, and one of them is going to be missing, and that's going to be the one that we need to find. So that's quite a shopping list, isn't it? Things I need to find. Let's see what we know in this story. I know dx by dt is 30, so I'll make them in red. I know that guy's 30. I know this guy here is 20, and they've actually asked me to find that guy. So that guy is meant to be missing, right? What I don't know yet is what the distance X is, what the distance Y is, and what the distance Z is, because they're all going to be numbers at 4 o'clock. So let's see if we can go hunting for each of those distances. If you tell me it's 4 p.m., isn't that just another way of telling me that it was 4 hours? And if you travel at 20 miles an hour, right, this direction, right, the Y direction, then wouldn't Y be 4 lots of 20 miles an hour? Wouldn't that be 80 miles? Are you comfortable about how I got Y is 80 then? Now, what about the X, right? Well, the X is this guy, and it's traveling at 30 miles an hour. So won't X be 4 lots of 30, which is what, 120 miles? So far, so good. Now, all I need to do is find out what number Z is. And you have to be a little bit careful. So I'm going to redraw a kind of snapshot version of this triangle. I know that this number here is 80. I'm trying to find that number. And I don't, well, let me say what it's not. That number there is not 120. Isn't that number 150 take away whatever X is? So are you comfortable that that's actually a 30? 150 take away X. Okay, so when you're finding Z, it's not, oh, right angle triangle, one side's 80, one side's 120, what's the third one? It's a little bit sneakier than that. One side is 80, isn't this side only 30? 120 off of that, right? 30. Right, Pythagoras, z squared is 30 squared plus 80 squared, so that makes z the square root of whatever that is. And so 30 squared plus 80 squared gets me 7,300. And I know that's a horrible decimal. I'm not going to worry about it. I'm going to let the calculator deal with that later. So I'm quite happy just to leave it. I'm not even going to make it look pretty. Just leave it. Right, let's return now to our connecting equation. And shouldn't we now differentiate with respect to t? Right, that's the next stage. And this one has its own little idiosyncrasies that we need to deal with. Let's do the easy bits. You differentiate this guy, you're going to get 2z dz by dt. If you differentiate this guy, you're going to get 2y dy by dt. Now we got the weird one. I'm going to differentiate 150 take away x all squared. And I'm going to differentiate it with respect to t, which is kind of a two-stage process. Don't you differentiate it with x first and then just finish with the dx by dt, right? So forgetting about the t's, just differentiating this the normal good old-fashioned way, isn't this technically a chain rule? It's 2 150 take away x's to the power of 1 times the derivative of the inside function, which in fact is the number -1. Are you comfortable where that extra -1 came from? And then you can finish with dx by dt. So that one's a bit ugly, wasn't it? You had to do a little bit more to make it happen. Right, let's put in what we know. 2 times z times the unknown guy that we're going to get, him, 2 times 150 take away x is 150 take away 120, so that's 30 to power of 1, times -1, times dx by dt, which is 30, plus 2 times y, which is 80, times dy by dt is 20. Now, as big and ugly as that is, isn't that basically just a whole load of numbers that the calculator can deal with? And again, I'm not going to make any attempts to make things look too pretty. But if you multiply this guy by this guy, you get 900. Double it, you get 1800. And then stick a minus in front of it. And if you do this one, you get 100, you get 16, you get 32 of those guys. And it's going to be over that. So I'll go to my calculator, put a little bracket around it, -1800, add 3200, divided by, put a bracket around it, 2 times the square root of 7300, and the answer I get is about 8 point, what do they want? I don't know. I think it's 2 decimal places, so 8.19, and the units were kilometers per hour. So as this one travels in and this one goes north, the distance between those is going to grow at the rate of roughly 8.19 kilometers an hour. Can you imagine as one goes this way, as one's coming in, isn't that one going to travel a lot that way? And so the distance between them just gets bigger and bigger. And how much bigger? Well, at that snapshot in time, at this speed. Any questions about that particular one that we just did? The ones that we have left to do, and I think there's 1 or 2, I'm not sure how many, let's check. Oh, good. There's only 1, so that's going to be perfect timing. Is to do with two things moving in different ways and how far apart they are. So question 14 has two cars moving from the same point. Okay, so here's a point. One is traveling south, so one of them's going to go this way, and I'm going to call that distance x. And it's going to go at a speed of 48 miles an hour. And the other is going to travel this way, because that's west. I'm going to call that y. And it's traveling at a speed of 20 miles an hour. And I'm not going to call that negative. And the reason why I'm doing this is that we're really only talking distances here in this particular story, right? That's going to get bigger, so positive works. So at what rate is the distance between them? So the distance between them is going to be that guy, right? So I probably should draw another triangle. I'm going to call this x. Why did I do that? That was silly. The good news is that I could stick to those variables, right? And it would work. And since I've started, I'm just going to keep going. Could have called them A and B or X and Y or anything, it still would work. So, okay. So I'm just going to live with my mistake. That distance is Z. And we're being asked to find what the rate at which they're moving away from each other. And we're doing it, the 3 hours. Now, when you look at this triangle, it's actually a lot easier than the previous one. Would you agree it's that? Pythagoras. Now, I need to know X, I need to know Y, I need to know Z, I need to know, or hopefully, one of these guys I won't need to know. But this is my list of things, right? X, Y, and Z and 3. Now, at the 3 hour mark, since this is X and this is going at 48, this will be 3 times 48. So after 3 hours traveling at 48 miles an hour, you would have done 144. So that's what X is. Y is 20 miles an hour. So 3 times 20. And that would be, after 3 hours, that would be 60 miles. Now, if you want to get Z, don't you have to do a little bit more work? That's going to be 144. And that is going to be 60. So wouldn't I just use Pythagoras to find out the missing number for Z? Right, that's just a little snapshot. X is this, Y is this. These are numbers, so Z. Right, this is an instant in time. So I'm just going to do that in my calculator. It's going to be the square root of 144 squared plus 60 squared. And the answer I get is, oh no. Look at that. That is amazingly nice. Don't you normally get just some ugly square root that you just have to deal with? But actually, okay, I can live with that. Didn't do anything silly. No, 144. Okay, that's cool. Dx by dt is 48 because you told me. Dy by dt is 20, and we're being asked to find that one. Doesn't everything match? I know everybody except one thing. All right, so I know this is going to finish well. Differentiate now with respect to t. You get 2z dz by dt. You get 2x dx by dt. And you get 2y dy by dt. Not really that weird. Right, time to put in numbers. 2 times 156 dz by dt. 2 times 144 times 48, 2 times 60 times 20. So dz by dt should be all of this divided by that guy. So I didn't do anything. I'm going to let the calculator do it all. When you're doing this, you better put a bracket around the top and then just go 2 times 144 times 48. Add 2 times 60 times 20. Close the brackets, that's the top done. Divided by, put another bracket, 2 times 156. And the answer we get is 52. And the units miles per hour? Yeah, miles per hour. And that is just an amazingly nice answer. And normally you're going to get decimals, but just the way the numbers come out here, isn't that really nice? So can you imagine somebody going that way at 20 mile an hour, somebody that's going that way at 48 mile an hour? How far apart are they going, right? What's the rate at which they're moving away from each other, you know, as a direct line as the crow flies? And the answer is 52 miles per hour. Miles. Well, can we pretend, not that I've ever done this, that I hit the wrong buttons in my calculator and I got the answer 520, right, 520 miles per hour. If you look at context, would you agree that based on these numbers, or if you like these numbers, but wouldn't that be silly? I mean, what's the worst that these two things could do? Wouldn't they be to go in total opposite directions? So isn't the biggest number, theoretically, the biggest number would be 68 miles an hour, right? You can't go any, you know, and they're not even doing that, right? They're at right angles. But if you went this way, that would be it. So I wouldn't, 52 seems reasonable, right? It's not quite these two guys added. If this number was 40, I would have looked at that question again. Because shouldn't the answer be somewhere between, you know, this number and the total? And so, you know, context can sometimes give you an idea that things don't look good. You know, if it's too big or too small. Sometimes sign can tell you. You know, if something's increasing, but you think the answer is minus 4.2, shouldn't you be worried? You know, if you read the story, you say, yeah, this thing's going to get bigger, and you get an answer in negative, that might be a clue. I think this is a very nice place to finish this. And I want to give you a little starter on tomorrow, a little taster. I kind of like this next section. I'm not saying everyone does, but I kind of like it. And it's section 310. And it's linear approximations. Well, history behind this. It's very easy for people to think that today is the way it's always been, right? I am old enough to remember there wasn't an internet, right? When I was a kid, internet didn't exist, at least not that I was aware of. Electronic calculators. When I started school, every calculation was done by hand. Every multiplication, every division, you had to do it by hand. Now we have calculators, right? So the world has changed quite a lot. So if I went and said to you something very simple, like, I want to get the square root of, oh, let's pick something nicer. I want to get the square root of 9.1. Everybody here would grab a calculator. Not one of you would say, oh, calculators haven't been invented yet. How did people in the past answer that question? How did they get the square root of 9.1? When I was at school, shows you my age, we were in the transition stage. I got my calculator when I was 16, right? And it had a square root button. And I thought this thing was a godsend. If I'd been a couple of years older, I would have to have done this by using a book. A book. In this book, they had square roots. And you would read 9, and then you'd read along, and it would be 0.1, and there would be the square root of 9.1, typically to 6 decimal places. The book was called a 6-figure table. And there'd be pages where you'd get cube roots, and there'd be pages where it would tell you what the sine of 42 degrees was, right? And, you know, it's just a book full of all these things done for us. So then you should think, how did the people who put the numbers into that book get the answer to the square root of 9.1? Right? Somebody had to figure a way of doing it. And we are going to figure out how they did that. And it's called linear approximation. So what you're going to do in linear approximation is that you're going to be given a function. And in this case, the function is going to be the square root of x. And you're given a value called a, which is really a number that is close to this guy, that makes a nice square root. Would you agree 9 makes a really nice square root? And the linear approximation function is called L of x. And its formula is f of a plus f dashed of a, x minus a. So in my example that I've just started with, f of x is the square root of x. I'm going to be able to, I'm going to have to differentiate it. So I'm going to call it x to the half. Its derivative then is multiply by the power, reduce it by 1, and then basically try and make it pretty, right? Style points. So the linear approximation function is going to be using 9. It's going to be the value of the function at 9 plus the derivative at 9, x take away 9. Do you see a is 9 in this case? Right? 9, 9, and 9. Now, I know what the value of the function is, right? F of 9 is the square root of 9, which is 3. So that guy's 3. Plus, I should be able to tell you what f dashed of 9 is. Can you just trust me that it's a 6th? Right, 1 over 2 times the square root of 9, 1 over 2 times 3, it's a 6th. So this is a 6th, x take away 9. And all I'm doing now is making it look pretty. 9 over 6 is 3 halves. And so it's 1/6 x plus 3 halves. And we call that the linear approximation function. And we wanted to find the square root of 9.1, didn't we? That was the problem. Well, the estimate is the linear approximation function at 9.1. Would you agree we can do that without a calculator? Although I'm probably going to do a calculator anyway, just for speed. It's going to be 1/6 of 9.1 plus 3 halves. And although that's cumbersome to do by hand, can you trust me? You can do it by hand, right? But for convenience, I'm just going to go 9.1 divided by 6, and then I'm going to add a 1.5, and the answer I get is 3.01 and a whole load of sixes. And in a six-figure table, 1, 2, 3, that would be the answer that you would see, may round it off to 7. Let's see how good it is. The real answer to the square root of 9.1 is 3.016620. Would you agree it's not perfect, but it's a pretty good approximation? And they had other means to improve on this approximation. And when you do Calc 3, there's a guy you're going to learn about called Taylor's series. What Taylor's series is, it just makes this formula bigger so that you can get a better answer. A linear approximation is linear. And the next one up would be called the quadratic approximation. And that would probably get you maybe that decimal place right. And the next one would be a cubic one, and that would get you probably the last one. And if you really wanted to be sure, you would do a T5, which is the quintic polynomial. So you can get the square root of 9.1 to 2 million decimal places if you felt like you wanted to spend the rest of your life doing one calculation. But theoretically, you could. And that's what linear approximation is. Let's see how good it is. The function I'm going to deal with is the sine of x, and I'm going to center it as 0 because that's a very nice number to get the sine on, right? And I would like to get an estimate for the sine of 0.123456. Okay, so that's my goal. Find the linear approximation function and use it to estimate what the sine of that guy is. Okay, Tess, I'm putting you in this spot. How many decimal places would you be impressed by, right? So that last one was good to 4. How many decimal places would you be for a sine function?
The 6 that were in your book.
You're going for a 6 that was in my book. God, you're a taskmaster. Let's find out if we can get it then. The function was the sine of x. The derivative of that function is the cosine of x. The value of that function at 0 is the sine of 0, which is 0. The derivative at 0 is the cosine of 0, which is equals 1, which these are really nice numbers. The linear approximation function is f of a plus f dashed of a, x take away a. And that's going to be the value of the function at 0 plus the derivative at 0, x take away 0. And that guy is 0, that guy is 1, and that guy is basically the linear approximation function is just x. So if I want to find an approximation for the sine of 0.123456, according to the linear approximation, shouldn't the answer be 0.123456?
Mm-hmm.
So the sine function, at least when you're close to 0, has the same value as x. Right, I'll go into my calculator and we'll do a mode. This one I recollect. When I first learnt this, it kind of went, wow. Now you got to remember, we were doing tables in books, and the first calculator I got didn't have sines and cosines in it. It just had multiply, divide, square root powers, right? It could only do a limited number of things. So can you imagine what it was like when I saw, wow, let's see how good wow is. It's a sine of 0.123456. Okay, it's not as good as what Tess wanted, but that was 3 decimal places. That's still pretty impressive, isn't it? Now, suppose I choose a value that is closer to 0. How about 0.00121212, right? So shouldn't the answer be essentially 0.00121212, approximately? Oh, I've now got 8 decimal places. Are you impressed now, Tessa?
Yes.
So if you use a linear approximation function, one of the truisms is, if you pick numbers really close to this guy, you will get really good estimates. If you pick guys that are a little bit further away, you'll get like 2 or 3 decimal places. If you pick something like the sine of 1, you're probably going to be in trouble, right? It's just too far away. Now, to finish with, I want to show you geometrically what the linear approximation function was doing. So I'm going to type in sine x. And I'm going to try that again because I obviously hit the wrong button. There we are. There's sine x. I'll zoom in a little bit. Right, we're really only interested, aren't we, at 0. I'm now going to put in the linear approximation function, which was just basically x, wasn't it? Now, at 0, which is really all we're interested in, can you see why the linear approximation function is good at predicting the value of sine x? Because isn't the blue and the red very close to each other for quite a lot of values of x? If I zoom in even more, have we reached a wow yet? Isn't y equals x, for all intents and purposes, like 6 decimal places? Aren't they the same thing? And that's a pretty cool thing, to be able to estimate a function. So if ever your battery of your calculator disappears and you can't use it or you've lost it, couldn't you do linear approximation and at least get a rough guide of what the answer is? Does anybody actually know, and there's a kind of clue in that picture, does anyone here actually know what the linear approximation function is the same thing as?
Tangent line to the curve.
Yes, it's just a tangent line. So, you know those tangent lines, equations of tangent line questions? Couldn't they also be find the linear approximation at x equals 1 or x equals 2, whatever it happens to be in this case, x equals 0? That's pretty cool. Now, just for a few more, because we've got the time. Linear approximation is all you're going to deal with, right? Do you notice it starts drifting the further away from 0 you get? That's a truism. It ain't going to, don't use sine x equals x approximation when x is 4 radians, right? Don't do that. It's going to be miles out, right? But keep close to the center. In this case, the center is 0. You're totally good. I'm going to make this guy disappear for a minute and shrink this guy back. From 0 to pi, do you see there to there? Do you see that shape? Isn't that very like a quadratic? So if you were into Calc 3, we would show you the quadratic approximation, which basically would be a quadratic curve that would go through that. And the quadratic approximation would just be better for bigger values of x. In other words, you could get a little bit further away from 0 and still be good. Now, if I move to this side, can you see that you probably want a cubic approximation? And that would be called T3. And theoretically, you can do a T20, which would be a polynomial at degree 20. And what a degree 20 would look like, it would probably do all of that for you. You imagine the number of bumps you'd get in a T to the 20. That is such a fascinating thing. And I have nothing but admiration for Newton. You know, that guy, nothing. I mean, I guess they had abacuses. I'm not even sure if they knew about that, right? There was just nothing to help you do any calculations. Yet he still figured out the motion of planets and calculus and did calculations that if I gave them to you and said, do that by hand, you would have just said, I'm not doing math anymore, I'm going home, right? But they figured it out, and linear approximations was how they figured out how to do calculations. Like, you know, what's the sine of 46 degrees, right? What's the square root of 82, right? You had nothing to work with. I believe, but don't quote me on this, do you know the people who made these books with the numbers in it? They were monks. Their entire life was taking a linear approximation and calculating it and doing it. And again, don't quote me this, but I believe this is true. They didn't have one monk do it. They had 3 monks do each calculation. And then they would check. And if all 3 of them had the same number, that went into the book. Can you see why they chose 3 as an error check, right? And that was, I guess, the first earliest form of error checking. Now they have, you know, computer programs that do error checking for you. Okay, last name, I've kept you enough.